dear students, do you all know what happens when the lights go off? I'm sure you all know that. Just check how many applications in your house work on electricity and can we do without them? In fact, the impact of electricity in hospitals, government offices, private offices, banks, shops, just to name a few, is such that it is hard to think of modern life without them. Out of the 200 years of history of electricity, the first 100 saw observations and experiments, and the next 100 saw electrical gadgets being developed. In fact, the success of electricity lies in the fact that at the instant of the flick of a switch, you can have all the gadgets on. We shall therefore study today what constitutes electric current, how to express electric current, how does it flow in an electric circuit, what is an electric circuit, and what makes the electric charges flow. So dear children, let us now understand what constitutes electric current.
Just as flowing water constitutes water current in rivers, if the electric charge flows through a conductor, we say that there is an electric current in the conductor. In a metal conductor, such as copper, the free electrons are in a random motion between ions. Hence, there is no net flow of charge in one direction. However, if we provide energy to a conductor, we can obtain a directional flow of electron. A cell or a battery provides the necessary energy for the charges to move.
We know that the electric bulb lights as soon as the switch is on. What does the switch do? The switch provides a conducting link between the cell and the bulb glows. Dear children, we can therefore now conclude that the flowing electrons constitute electric current in conducting wire.
Let us now talk about how do we express electric current. Electric current flowing through a conductor is expressed by the amount of charge flowing through a particular area in unit time.
If a net charge Q flows across any cross-section of a conductor in time t, the current through the cross-section is I is equal to Q by T.
The SI unit of electric current is ampere, named after French scientist André-Marie Ampere, and SI unit of charge is coulomb.
1 ampere current is defined as the flow of 1 coulomb charge per second. Small quantities of current are expressed in milliampere or in microampere. 1 milliampere is equal to 10 raised to minus 3 ampere and 1 microampere is equal to 10 raised to minus 6 ampere. An ammeter is an instrument used to measure an electric current and it is connected in series in a circuit.
Let us now understand about the direction of an electric current in an electric circuit. We know that flow of electrons constitutes electric current, but Do you all know that electrons were not discovered when the phenomena of electricity was first observed? The direction of flow of positive charges was considered to be the direction of electric current. Although we know that electrons constitute electric current, even today the direction of electric current is taken to be against the direction of flow of electrons.
What is an electric circuit?
We have been talking about an electric circuit, but dear children, what is an electric circuit?
A continuous and a closed path of an electric current is called an electric circuit. An electric circuit is a combination of various electric devices and instruments. This electric circuit comprises of a cell, an electric bulb, an emitter, and a plug key. Let us now look at the symbols of various components used in electric circuits. An electric cell, a battery or a combination of cells, plug key or switch open, plug key or switch closed, a wire joint, wires crossing without joint, electric bulb, a resistor of resistance R, variable resistance or rheostat, emitter, voltmeter.
So dear children, till now we have seen
Flow of charges, electrons in particular, under the influence of a battery constitutes electric current in a conducting wire. Electric current, denoted by I, is expressed by the amount of charge denoted by Q flowing through a particular area in unit time t. That is, I is equal to Q by T. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, which are negative charges.
Let us now understand how to solve a numerical example using the relation I is equal to Q by T.
A current of 0.5 ampere is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. Here data that we have is I is equal to 0.5 ampere, T is equal to 10 minutes, that is equal to 600 seconds. Find charge, that is Q. Now, Q is equal to I multiplied by T. Substituting the given values, we get Q is equal to 0.5 ampere multiplied by 600 seconds. That gives 300 coulombs.
Let us now look at what makes the charges to flow. To establish an electric current, we need to establish the flow of free electrons. Imagine what is needed to establish a flow.
We know that water in a pipe kept flat on a table will not flow. However, if we lift an end of the pipe, that is, we create a height difference, the water starts to flow. Similarly, for flow of charge in a conducting wire, the electrons move if there is a potential difference along the conductor. This difference of potential can be produced by a battery consisting of one or more cells. The electric potential difference between 2 points in an electric circuit carrying some current is defined as the work done to move a unit charge from one point to another. Thus, potential difference V between 2 points is equal to work done W divided by charge Q. That is, V is equal to W by Q. The SI unit of electric potential difference is volt, V. After Alessandro Volta, an Italian physicist, 1 volt is the potential difference when 1 joule of work is done to move a charge 1 coulomb.
How does a cell produce a potential difference?
The chemical action within a cell generates the potential difference across the terminals of a cell even when no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in conductor in motion and produces an electric current.
Let us now understand the relationship between the potential difference across a conductor and the current through it by performing a simple activity.
To study the relationship between the potential difference across a conductor and the current through it, materials required are milliammeter, voltage source or a battery, rheostat, key, voltmeter, and a conductor. For connecting the components as shown in the experimental setup, we start with a voltage source. The positive terminal of the battery or the voltage source is connected to the positive terminal of the milliammeter. The negative terminal of the battery or the voltage source is connected to one terminal of the key. The second terminal of the key is connected to the fixed terminal of the rheostat. The variable terminal of the rheostat is connected to one terminal of the conductor. The negative terminal of the milliammeter is connected to other terminal of the conductor. To measure the voltage across the conductor, the voltmeter is connected parallel with the conductor. Note carefully that the milliammeter is connected in series and the voltmeter is connected in parallel. Now, the current through the conductor and the voltage across it can be measured by sliding the jockey of the rheostat. We change the value of the current in steps and note down the corresponding voltage in voltmeter. When the rheostat is at the extreme end, the milliammeter reads 0 and the voltmeter also reads 0. On sliding the jockey of the rheostat, the milliammeter now shows 125 milliamperes and the corresponding reading in the voltmeter is 0.625 volts. Repeating the above step, we enter our results in the observation table as shown. When current is 0, voltage is 0. Current 125 milliamperes, voltage is 0.625 volts. 150 milliamperes, 0.750, 175 milliamperes, 0.875 volts, 200 milliamperes, 1 volt, 225 milliamperes, 1.125 volts, 250 milliamperes, 1.250 volts, 300 milliamperes, 1.5 volts. In the last column, the ratio of voltage and the current has been calculated. Here, the current has been measured in milliamperes and the voltage is measured in volts. We therefore convert the current in milliamperes to amperes by multiplying the current value by 10 raised to minus 3 and then take the ratio V by I. Results. From the observation table, we observe that the ratio V by I is a constant ratio. We can therefore conclude that at constant temperature, the electric current I flowing through a conductor is directly proportional to the potential difference V across its ends. Next, we take a graph paper and mark the current I in amperes on x-axis and the potential difference V in volts on the y-axis. On plotting the successive values of current and the corresponding values of voltage, we get the points 0, A, B, C, D, E, F and G. We now join the points O, A, B, C, D, E, F and G. A straight line graph is obtained. Conclusion. The straight line graph shows the current I is directly proportional to the potential difference V.
Today, we have therefore learned the following points about electricity.
A stream of electrons moving through a conductor constitutes an electric current. Conventionally, the direction of current is taken opposite to the direction of flow of electrons. The SI unit of electric current is ampere. To set the electrons in motion in an electric circuit, we use a cell or a battery. A cell generates a potential difference across its terminals, which is measured in volts V. Relation between the potential difference across a conductor and the current through it.
I am sure, dear children, so now you have understood what is electricity and its importance. With this, I would like to conclude my class for today. In the next class, we shall see types of electric charges, what are conductors and insulators, Ohm's law. So, dear children, goodbye and have a nice day.